Hello and welcome to this video where today we're going to be looking at the specific charge of the electron. Specifically, this is the second video in the Turning Points playlist. It follows on from looking at how the electron was discovered. So now we're going to have a look to see how scientists very first started to think about how they could measure the properties of the electron. So we're going to do four things. What we're going to do is we're going to start with a little bit of revision. We're going to remember what a specific charge was. And then we're going to have a look at a couple of different ways that you can actually measure the specific charge of an electron. So we're going to look at start off by looking at just magnetic fields, and then we're going to have a look to see how we can combine electric and magnetic fields together to also measure the specific charge. So really we've got two or three different ways that we can measure the specific charge of this particular electron. So a little bit of revision first. The specific charge of a particle, you'll remember from your first year of physics, is often known as the charge to mass ratio. And what we do is we calculate it by looking at the charge of a particle and the mass of the particle. The charge is in coulombs, the mass is in kilograms. And to work out the specific charge, we simply take the charge in coulombs and we divide it by the mass in kilograms. So for example, a quick reminder of how you would find the specific charge of a proton. Well, what we would do is we would simply write, we've got the specific charge is the charge of the proton, so 1.6 times 10 to the minus 19 coulombs. And then we would divide that by the mass of the proton, so 1.67 times 10 to the minus 27 kilograms. We don't have to be massively specific in the same way that we do for nuclear physics in this case, so this number will do. And when we put that in our calculator, we end up with a number that is 9.6 times 10 to the power of 7 coulombs per kilogram. Now this number was particularly important at the time when they were looking at cathode rays and things, because at the time this number was the largest specific charge of any particle. So really what this meant was that provided the charge was the same, it meant that it really had the smallest mass. They didn't know it was a proton at the time, they simply knew that it was the particle that had the largest specific charge. So that was from a historical point of view, that's really, really important. So what we're going to start off by looking at is we're going to start off by looking at what happens when we try and measure the specific charge. Well, the first way we can do this is by looking just using magnetic fields. And what's really important is to know that is basically to know how these things were created. So what we've got is we've got basically some thermionic emissions. So we've got a power supply here that provides a heat current to a heating element. Essentially, the electrons gain more kinetic energy than they need to stay inside the metal. So they are able to be freed from the surface of the metal. There's then a high voltage power supply which is also connected to this, and so you've got an anode up here and a cathode up here, so the electrons are accelerated in this way. So what's going to happen is the electrons are going to come out of here and they're going to have a velocity in this particular direction up here. Now, as we've seen in magnetic fields, if we have a charged particle travelling at 90 degrees to a magnetic field, and in this case the magnetic field may well be going either in to the page or out of the page, then this thing will go in a circle. So this kind of shows you a very rough drawing of a three-dimensional projection of this particular thing over here. So these circles are meant to represent circles of coils of wire that we can't see on here. They're on either side. They provide a magnetic field that goes through like this. So we're thinking about magnetic fields that go in either in or out of this particular paper. The velocity is at 90 degrees at that, so therefore the force is at 90 degrees to both of those, so we'll be in this direction over here like this. So it'll be towards the centre of the circle for this point. So this makes it go in a circle. Now we need to be able to explain, the very first thing we need to be able to do is explain why it goes in a circle. So these are the important points. We've got a force, and that's at 90 degrees to the displacement. That means no work is done by the force. And if no work is done by the force, because if you remember, work done is equal to the force times the displacement times by the cos of the angle between them. Well, obviously if the angle is 90 degrees, cos is 0, so the work done is 0. So if no work's done, that means the kinetic energy of these particles is remaining constant. That also means that the acceleration is also at 90 degrees to the motion, and so therefore the speed is constant, which basically means that this thing carries on going round in a circle continuously. So we can start to think about how we could look at the specific charge of the electron. So if we think about the forces that are acting on this particular particle, we have a magnetic field here, and we've got a charged particle in the magnetic field. So the force acting on our charged particle is equal to the magnetic flux density multiplied by the charge of this particle. So I'm going to write that as an E to make it very clear that we're looking at the charge on the electron, multiplied by the velocity of the particle. So that's our equation that links the force with the charge and the magnetic field strength and so on. Because this is also going in a circle, then this force, of course, is also a centripetal force. So we know that that's equal to mv squared over r, where m is the mass of our particle, v again is the same v here, so it's the velocity or the speed of the particle actually, and r is the radius of the circle that this thing is travelling in. So if we put these two things together, then as we've seen before, we can rearrange this and we get that the radius is equal to mv over b times e, like that. So this is a constant radius because the mass is constant, velocity is constant, the magnetic flux density is constant, and also the charge on the electron is constant. Now so far this doesn't really help us actually think about how we can calculate the specific charge. So now we'll bring in another relationship. So we know that for the electrons that are being accelerated through this potential difference over here, what we've got, if we were able to zoom in, is we've got we've got the cathode here, which is our wire that's been heated up, and the electrons are freed from here, and this is a positive anode with a little hole in, and the electrons accelerate this way, in the same way that they did in the first video. So the potential difference between here we can actually measure, and so what we're going to assume is that this is at 0 volts and this anode has got a certain potential, so the potential difference between here we're going to call VA. It's basically going to be, we're going to call that the anode potential difference. So we can think about this. So what we can think about is we know that these things go at a constant speed around here, so the speed that they come out of or past this anode at is equal to the speed that they go around the circle at. So we can work that out, or we can have a relationship. So we know that E times the anode potential difference, so that's the work done by the electric field, is equal to the kinetic energy of our electrons, like that. So we've got the work done by the electric field is equal to the kinetic energy that's gained by these particular particles. So what I'm going to do now is I'm going to write the specific charge. The specific charge is the charge over the mass, so that's E over m. So I'm going to rearrange this equation to get E over m. And if I do that, E over m equals v squared over 2 times this anode potential, like that. So this is the anode potential here, or anode potential, that's the potential difference between there in volts, and this v squared here, so we need to be careful with our v's, this v squared here is the velocity. So what I could do is I could take this equation that we know, and we can rearrange this and get the velocity from this, so we'll do that. So the velocity is equal to, if we rearrange this, we multiply by BE, so we get BER, and then we divide that by the mass. So we know what the velocity is. So we can take this velocity and we can place that into here. So we've got this part, so we've got 1 over 2 lots of the anode potential difference multiplied by V squared. So if we square the whole of this thing, we get B squared, E squared, R squared over M squared, like that. So we've got another E and an M over here, apart from these ones are squared. So if we collect all of these terms together, and we basically make E over M the subject, in the end, what we end up with is E over M is equal to twice the anode potential difference divided by B squared R squared, like that. So in terms of actually measuring this thing, the potential difference is easy to measure because that just comes from this particular power supply over here. R is the radius of our circle, so that's just the radius of this thing over here, so that's easy to measure. You can almost just use a ruler for that. The tricky one to measure is the magnetic flux density, this one, but if you do know that, then you take these three things, and if you put them into this equation here, it'll tell you what the specific charge of your electron is. So that's one way you can do that. It involves basically circular motion, the force on a charged particle in a magnetic field, and the concept that the work done by an electric field is equal to the kinetic energy gained by some particles. You just have to be a little bit careful with your V's, and so if we start to put some subscripts on, then that'll help. So the next thing we can do is think of a different way to calculate the specific charge on our electrons. So this is essentially the same setup that we've just had. What we've got is a magnetic field from these two coils of wire. They pass through here. But what we've done now is, instead of just having the magnetic field, we've basically also got these two metal plates up here. And we've attached these metal plates such that the magnetic force is balanced by the electric force. So what we've got is we've got our electrons here, and the magnetic force is in a certain direction, and the electric force is in exactly the opposite direction. So if we could actually look at these, although they're not, these forces aren't vertical, what you'd have is you'd have your magnetic force, for example, downwards, and you might have your electric force from your electric field upwards, like that. And because these are now balanced forces, this thing goes in a straight line. So what we've really done is we've used this thing, we've used the electric field to straighten out this actual these electrons that were going in a circle, and they now go in a straight line. So again, we can use this to think about how you might measure the specific charge. So if we think about this, what we've got is the electric field upwards, or the electric force upwards. The force from an electric field is simply equal to the charge of the particle that's in the field multiplied by the electric field strength, like that. As we've already seen, the force from the magnetic field is equal to the magnetic flux density multiplied by the charge on the electron multiplied by the velocity that goes at. And if they're going in a straight line, the resultant force is zero, so these two things are equal. In other words, the charge on our electron multiplied by the electric field strength is equal to the magnetic flux density times by the charge multiplied by the velocity. These charges cancel out because they're the same charge, so actually that gives us a very straightforward way of actually calculating the velocity now. So the velocity is simply equal to the electric field divided by the magnetic flux density. So this gives us a much easier way of actually calculating the velocity. So what we can do is, because the electric field is really easy to actually calculate, the electric field strength, if you remember, for two parallel plates is equal to the potential difference between the plates, and I'm going to put a little p on here simply because I don't want to get this potential difference mixed up with the potential difference from our anode over here, divided by the distance between them, and the distance is this distance between the plates. So what we've got is, if we want to put that into there, then our velocity now is of our particles is equal to E, which is this potential difference over D, and then we're also dividing by the magnetic flux density, like that. So what we could do is we could take exactly the same equation that we had before for our electrons going in a circle, which is R equals mv over b times E. And basically we could put in our velocities. So I'm going to stick with this one simply because it's easier than this one. So that's equal to m over the magnetic flux density times the charge multiplied by the velocity, which is E over b. And if we just simplify that a little bit, we get mass times electric field strength over b squared E, like that. So we've now got an m and an e in here, so we can rearrange this equation to get E over m. So E over m is simply equal to, if we take this, is basically equal to E over b squared r. So that's a much simpler way of actually calculating the velocity than it was in the last example. So that's the reason that this is done as opposed to this one. So although you can do this, it's actually a little bit more complicated. This one is much easier because it's actually very easy to calculate the electric field strength. So you could take your electric field strength from here, which is the potential difference between here and the distance, and calculate the electric field strength, and then simply put it into this equation here, and that will give you a second way of calculating the specific charge on our electron. So what we did then is we had the magnetic field making these things go in a circle, and then we kind of straightened them out by applying an electric field. You can also think about the opposite way of doing that. So what we're going to think about is what happens when we have an electric field like this, and then we use a magnetic field to straighten this thing out. Now the very first thing we need to do is to think about why it's got this shape, because the specification from AQA wants us to actually know or understand why it has this parabolic shape. So this is the reason why. What we've got in this case, so I've chosen again this top plate to be positive. The electrons are going to move upwards in a parabolic shape like that, and then when they get out of the electric field, they then go in a straight line on either side, and they're coming this way, so they go straight and then parabola and then straight again. So the reason they have this shape, and these are the marking points for these types of questions. So the force is upwards because the top plate is positive, the electrons are negative. That's one marking point. Next marking point, that means the acceleration is upwards because the force is upwards. That means the vertical component of the velocity increases. So this vertical component increases, but there's no force horizontally, and so the horizontal component remains constant. Finally, that means that the angle of deflection from this horizontal gradually increases, and so you end up with this parabolic shape. So they're the marking points for actually explaining why it's got this shape, but we also then want to look at how you would calculate the specific charge if you've got an electric field, and then you apply a magnetic field. So it's kind of like exactly the opposite thing to what we've just done. So if we just get rid of these marks, okay, if we kind of have a think about this, what we've got while it's in the electric field, this thing has moved a distance d up here, like that. Actually, let's not call it d, let's call it y instead, because we don't want to get it mixed up with the distance between these plates. The length of the plates we'll say is L. So the length of these plates is a capital L, and the distance between the plates, so that's why we didn't call the other one D. The distance between the plates is D. So what we can do is we can basically say that this thing has moved up this distance. Why? And we can start to think about how, because this is basically constant force, it's a little bit like a projectile. So we can kind of think, okay, if we want to know the time, for example, that this thing is inside here, that's going to be equal to L over the velocity. So it's simply the distance divided by the velocity tells us the time that this thing's in here. We also know that acceleration is equal to, because of Newton's second law, and F equals ma, that acceleration is the force over the mass. And that's equal to the force from the electric field. Well, the force from the electric field is equal to the charge multiplied by the potential difference between our plates, because that's the thing that's providing the electric field, divided by the distance, d, between the plates. And then we've got this extra m over here. So the acceleration's got an e and an m in it already. So we can rearrange this thing, and we end up with the specific charge of our electron is equal to the acceleration multiplied by the distance between these two plates, divided by the potential difference between these two plates over here. Now that's fine, apart from the fact that actually calculating the acceleration of the electron is actually going to be really difficult. So we're going to change it a little bit, and we'll try and go back and think about, see if we can get a velocity into here. So let's think about this particle from a vertical point of view, because it is very much like a projectiles type question. So the force is upwards. If we think about this, then if we just use S equals ut plus a half at squared, then what we can do is we can think about what's going on here. So S is, if we're thinking vertically, is the distance it moves upwards, so that's y. That's equal to ut. Well, when it first came into here, the vertical component was 0, so that's gone. That's equal to a half times the acceleration multiplied by the time squared. So, and because we know that the acceleration is basically given by this thing, we've also got a term for the acceleration here. So that implies that the acceleration, if we rearrange this thing, because we're going to put it into here, the acceleration is equal to 2 times y over t squared. So we simply just rearrange this equation. But we know from up here that t is equal to L over v. So if we put that into here, so we can keep on going. So the acceleration is equal to 2y, and then we're dividing by t squared. So we've got a velocity squared over an L squared, like that. Finally, we end up with, because what we're going to do now is we've got an acceleration here, so we could work out the acceleration if we knew the velocity. We could take the acceleration, put it into here, and so therefore we know everything we need. It's simply that we need this velocity. So what we're going to do again is we're now going to take a magnetic field and we're going to straighten this out. And as we saw before, if once the resultant force on this is 0, so this thing straightened out, then we automatically know that the velocity is equal to E over B, because we've now got this magnetic field that's actually doing the same thing. So what we would need to do if we were calculating the specific charge from an electric field that's then straightened out with a magnetic field, what we'd do is first of all we'd calculate the velocity. That would be our first thing, by looking at the electric field and dividing it by the magnetic field strength. We'd then calculate the acceleration by putting that into here. Well, y is that distance there, which we can measure. The velocity we can measure from the fields. L is simply the distance of the plate, so we can work out the acceleration. We then take that number, we put it back up into here. D is the distance between the plates. Vp is the potential difference between the plates, and if we do all of that, then we end up with the specific charge on the electron. So we've got three methods. We can either look at this method, we can look at this method here, which is fairly straightforward, where we thought about straightening up a magnetic field that was using electric field, and then firstly, in this particular case, we looked at just what happens when the thing goes in a circle. Okay, so we're going to do one really quick worked example. So what we've got is we have a beam of electrons that's accelerated first of all through a potential difference of 1900 volts. So that's our anode potential, because it's the anode that does the accelerating. We then find that these electrons go in a circle and the radius is 2 centimeters, and that the applied magnetic field is then measured, and we find that the magnetic flux density, so that's our B, the magnetic flux density is 7.35 times 10 to the minus 3 Tesla. So we've got radius, and we've got magnetic flux density, and we've got an anode potential. So if we go back here, if we look at this, we can calculate the specific charge using this equation here. So we've got twice the anode potential divided by the magnetic flux density squared and the radius squared. So if we simply write that down, specific charge of our electron is equal to twice the anode potential divided by magnetic flux density squared and the radius squared. So we just put our numbers in. So we've got 2 times 1900. We divide that by this squared, so we've got 7.35 times 10 to the minus 3 squared. And if we extend this line, also 2 centimeters squared, but obviously this thing needs to be meters, so 0.02 squared. And if we simply do that on our calculator, then it's not a big surprise that we end up with 1.8 times 10 to the power of 11 coulombs per kilogram. So that gives us the specific charge of our electron. So in some respects, this is actually really quite simple, because we're doing the same thing over and over again. All we're doing is we're looking at what the specific charge is, and the important thing about that is that you always end up with an E over M and use that as one complete thing. And then you've got three different situations. One where you've got just magnetic fields going, and it makes the electrons go in a circle, and then these two here, where basically you take, if you've got an electric field, you straighten it out with a magnetic field, or you have a magnetic field and you straighten it out with an electric field. The equations are quite complicated, and actually what you're expected to do is you will be expected to derive each one of these, this one, and finally this one, actually in the exam. So very often they say show that the equation is given by this here, and then calculate the specific charge of the electron. So that's it from me. Thank you very much for watching, and I'll see you again soon.